Okay, so we're going into kind of the second part of energetics or thermochemistry today. So the main topic that they call it is Hess's law. We're not actually going to get into Hess's law until next time because I had to kind of shorten things today a little bit. So the videos are already up there to kind of get started, but we're only going to focus on the first part of this today. But basically, what we're going to see here is that if I want to calculate or determine the enthalpy change for a reaction, if I do that reaction in multiple steps that kind of go in order or in like a series, so if it's carried out in a series of steps, what I can do is I can add up the enthalpy changes of all the individual steps. So it's kind of like if I want to go from like point A to point C, I can either go straight from A to C if I know that information, but if I don't know that, maybe I know how to get from A to B and then B to C, and I can add those two together, and that will give me how to get from A to C. And so that's what we're going to see when we're doing stuff this week is that we can take individual reactions, and if we know their enthalpy changes, we can add them together to get the reaction that we want. So it's kind of like a puzzle sum this week when we get to that later on Thursday. And so what we're going to see is we're going to use Hess's law next class, not today, but we're going to use Hess's law to calculate enthalpy changes. What we're going to look at today is this second bullet here. We're going to actually calculate enthalpy change values using what we call enthalpy of formation data, and we'll talk about what that means in just a minute. And then the other thing that we'll see on Thursday is where we are going to determine the enthalpy change when it's the sum of multiple reactions with known enthalpy changes. So if you need to look up numbers for the calculations that we're going to be doing today, they're called enthalpy of formation. And so that's why it has the little F here in the symbol. That little subscript F is for formation. If they don't give you numbers in the problem for enthalpy of formation calculations, you can look them up in the data booklet in section 12. And what we're going to be doing today is we are going to be using this equation right here. It looks really complicated. It's really not. Okay, it's just adding and subtracting. Okay, they just kind of use all these symbols to shorten it. So here's what we are going to do today. Today we are going to do this one, and we are going to do this one. Okay. The other two, we're going to push them back to Thursday so that we have enough time to get through them since we were short on time today with the fire drill. Okay. So going to our page that we're going to focus on today. So here's the term that we're going to look at. It's called the standard enthalpy change of formation. So it's enthalpy, the capital H, it's a change in enthalpy. It's standard, that's why it has the little zero symbol, but then it's the formation, so it has this extra little F symbol down here. So that's kind of all the different parts going into that symbol. Is standard is the little zero, enthalpy is the H, change is that triangle delta sign, and then of formation means we have the little letter F. Now, last week we had standard enthalpy of combustion or standard enthalpy of neutralization, and their symbols looked almost exactly the same. The only difference was like for combustion, it had a little C down here, and for neutralization, it had like an N down here, I believe it was. Okay. So the symbols will all look the same except for that little subscript letter, and that will tell us what which one of the enthalpy changes we're talking about. Okay. All right. So formation is what we're focusing on today, and the definition of enthalpy, the enthalpy of formation, it has to do with what it sounds like. It has to do with forming a compound. Formation. You're forming a compound. So it's the enthalpy change when 1 mole of a substance is formed from its elements in their standard states under standard conditions. So if I took, if I wanted to know the standard enthalpy change of formation for water, then I would have to figure out, okay, if I have hydrogen and I have oxygen and I put them together and I make 1 mole of water, what's the enthalpy change when I form 1 mole of that water? Okay. And so somebody somewhere did all of this measuring and experimentation, and they figured out all the standard enthalpy changes of all these different common compounds like water and carbon dioxide and a lot of other compounds. And so they're all, like I said, in that data booklet on table 12 or section 12, I think it was. And so if you need to look them up, they're in there. So a lot of times though, they will give them to you in a problem like right here. So in the ones we're looking at today, it says calculate the enthalpy change for each of the reactions below given the data in the table. So sometimes they'll give you a data table like this with just the ones that you need to use for your calculations. Sometimes they might not. Sometimes they'll tell you, look in section 12 in your data booklet. Okay. So you just need to know that if they don't give them to you, that's where you can find them. The other thing I want to point out, there's an important thing right here. Elements have a standard enthalpy change of formation of 0. So if there are elements in your chemical reaction anywhere they're not part of a compound, they're just elements by themselves, they are always 0. They don't have an enthalpy change of formation value. Okay. And that's important as we're going to see here in just a minute. So the way that this works is it'll read similar to this problem. It says calculate the enthalpy change of each of the reactions below given the data in the table. And so if I look at this table, I can see here's the symbol. So I know I should be able to tell from that symbol, oh, they've given me enthalpy of formation values. So this is the process that I need to use to calculate the enthalpy change. And so I'm going to use this equation right up here. And like I said, it looks kind of like a complicated equation, but it's really not, okay? This symbol right here kind of looks like a weird E. This is a Greek letter. It's called sigma. And what it translates to, it translates as sum of, S-U-M, sum of. So anytime I see that symbol anywhere in any kind of equation, it could be chemistry, physics, math, it's used a lot. Anytime I see that, that means I'm adding something together. I'm adding something up because I want the sum of something. So it's here twice in this equation because we're going to add up two different sets of numbers, okay? I'm going to add up all of the enthalpy change of formation of my products. I'm going to add all of them up. And then over here, I'm going to add up all the standard enthalpy of formation of my reactants. So what I'm going to do is I'm going to look at my chemical equation and I need to identify, okay, where are the products and what are they? And then I'm going to look up their enthalpies of formation on the data table that they give me, and I'm going to add them all together. Then I'm going to do the same exact thing for any of the chemicals that are on my reactant side. And then once I've added all my products together and I've added all my reactants together, the last thing is, and I kind of wrote over it with my red circle here, but right here in the middle, there's a subtraction sign. Because remember, calculating delta H, delta is change in. That means I'm always usually going to subtract something. Okay. So how this works with an actual problem. Okay, I'm going to come down here to my data table. So here we're going to do number 1 together, and then 2 and 3 are going to be what you're going to work on your own. So how this works. Number 1, if I'm asked to do this with delta H of formation, which I am because I can see that's labeled in this data table, first thing I need to do is check, are there any elements in my chemical reaction? So I have, here's a reactant, here's a reactant. I'm going to do that. So I have 2 reactants and I have 2 products. Okay. Are any of those 4 things an element that's not a compound? What do you think? So remember, elements are going to have all the same type of atom. So compounds will have different element symbols combined. So right here, this oxygen, even though it's O2, even though it's 2 oxygens, it's still just one single, one element. They're both oxygens. So anytime I see elements like that, I can automatically kind of cross it out because that is not going to affect my calculation because as we said up here, the elements have a standard enthalpy of formation of 0. So they don't go into my calculation. Okay. I only need to worry about my compounds. So I'm going to come down here and our equation, I'm going to look at it one more time. Okay. First thing I need to do is I need to add up all of my products. Okay, that's over here. That's this side. So I need to look on this data table and find the formulas for my products and look up what's their enthalpy of formation value. So if I come down here, I kind of underline them in red. So CO2, here's CO2. One thing you want to be careful of when you're looking up your values, make sure not only is the chemical formula the same, make sure the state is the same. Okay, on this data table, this doesn't really matter because they give us only the information we need. But if you're looking up on the data booklet, there might be like a CO2 that's gas. There also might be like a CO2 that's liquid, or water. It could be water that's a liquid, or water that's gas because it could be steam, or it could be water that's solid because it's ice. So just be careful when you're looking up that not only is the chemical formula the same, but the state symbol is also the same because the number will be a little bit different. So CO2 is right here, negative 394. So I'm just going to label them for right now. So this one's negative 394. And then my other product is water, H2O. So here's water. It's negative 286. Okay. And then on the reactant side, we already crossed off oxygen because that's an element and it's going to be 0. So I just need to look up what is the enthalpy of formation for my other reactant. It's C5H12. And it's right here. It's negative 173. Okay. So now that I know the values for each one, I can set them up in this equation and do the calculation. So I'm going to come down here so I have more room to write so you can see. So I always do products first because it's always products minus reactants. So for my CO2, we said the CO2 was negative 394. Here is the catch, okay? That negative 394, that's for 1 mole of carbon dioxide. So that value is only for 1 mole. In our equation, there is a 5 coefficient in front of CO2. That means there are 5 moles in our reaction. So that means this negative 394 needs to be multiplied by 5, okay? So you always multiply your enthalpy of formation value by your coefficient for that substance in your equation. Then I'm going to add that to my other product, which is the water, which is negative 286. But it also is going to be multiplied because it also has a coefficient. It's going to be multiplied by 6. And so I'm going to put kind of brackets around this whole thing because that's the sum of my products. So I'm going to do their enthalpy of formation value multiplied by their coefficient for each one. And then I'm going to add them together. That's my product side. Now, if I go back up and look at my equation, okay, that's this side. That's the sum of the products. Now I need to do this side. I need to do the sum of the reactants so that I can then subtract them. So the reactants for this one, it's going to be a little bit easier. So I'm going to go ahead and put subtract in here. The reactants are going to be a little easier because number one, we already got rid of oxygen because oxygen's 0. So the only reactant we have is this negative 173 for the C5H12. And then if we look, it does not have a coefficient. Okay, that means there's just 1 mole of it, which means that it doesn't need to be multiplied by anything. It's just negative 173. So if you don't have a coefficient, then you don't have to multiply your enthalpy of formation value by anything. Okay, so if I kind of go through now and simplify and just do the math on this, what do I get for, let's see, we got negative 394 times 5. That gives us negative 1,970 plus, and then for the water, negative 286 times 6. That is negative 1,716. And then we're subtracting negative 173. Okay. So this is where you got to be careful of like your negative signs because this is where people have trouble. first off, these, I can just add these together. They're in those brackets. So I need to total up. I need to get the total for all of my products. So negative 1,970 plus negative 1,716. So I get the total for the products, I get negative 3,686. Then I still am subtracting my reactants. So I get the total for my reactants, which on this one was just negative 173. We didn't really have to do any other math or multiply anything there. But what happens when I subtract a negative in math? You know?
What was the question, Miss? I'm sorry, it keeps cutting out.
Oh, I was saying in math, what happens when you subtract a negative, like right here? So we have a subtraction, but then we have a negative number. So in math, when you subtract a negative, what ends up happening?
You like add them?
You add them. Yeah. So a lot of times here, if you're subtracting and then your reactants are negative, you can go ahead and just change it to adding. So now I'm just adding 173. Okay. So then I have that negative 3,686 plus 173. And then that's going to be my final answer. Oh, I keep going back up to the other part. Okay, there we go. That gives me negative 3,513, and it's kilojoules times mole to the -1 because it's kilojoules per mole. So that's essentially, that's the process for what you're doing on your other two practice ones on here. And then next time we will pick up and finish kind of the rest of the next couple pages with Hess's law. But essentially when you're doing this, you know, you just have to remember you always do products minus reactants, and you have to add up all your products, add up all your reactants, and then subtract them. Okay. And then when you're doing that, adding up and totaling up all your products and all your reactants, you just have to make sure that when you check your chemical equation, because if there's a coefficient in front of one of the formulas, then you have to multiply its enthalpy of formation value by that coefficient before you add all of them up to get the total. And so it makes sense that we're getting a negative number, because if I go back up here to number 1, this is a combustion reaction. In fact, all of these on here are combustion reactions. Okay. Combustion is where you have some kind of hydrocarbon compound. So it's compound with carbon and hydrogen. It reacts with oxygen because you're burning it, and you always produce carbon dioxide and water. So all of these have that same pattern. The only thing that's changing is the amounts of carbon and hydrogen in that first compound. And so anytime you see something that's doing this pattern, that's combustion. And we talked last week in our notes about how all combustion reactions and all neutralization reactions, they are always exothermic. They always release heat. And that means that they should have a negative delta H value, which we just calculated. It's negative 3,513 kilojoules per mole. So that's just one way that if you kind of remember those definitions of combustion and kind of their properties, that you should be able to check yourself, because if you were to get a positive number, then you should know, hey, that's not right. There's something wrong here. So like I said, that's where we're going to stop today. So it's kind of short, but we'll pick up on Thursday with the next page, and we'll talk about Hess's law. And this is really, if you want to kind of do you can get ahead, the videos are already on Canvas, but we'll go through it together on Thursday so we can take a little more time, because some people find this easy. Some people find it a little confusing at first, because really, to me, it makes sense because my brain works very logically, and it's all about sort of making a puzzle fit. Okay. And so once you kind of see it worked out and you practice it a little bit, it starts to make more sense. But in the beginning, it can be a little bit tricky.